Hello, and welcome to the lecture on 2.8. Today we're going to talk about one-to-one functions and inverses. Let's go ahead and start with a definition. A function with domain D is called one-to-one if no two elements of D have the same image. What that means is f of x1 is not equal to f of x2 whenever x1 is not equal to x2. So, if we have two different elements in the domain, then they map to two different elements in the range. That's what it means for a function to be one-to-one. We map one element from the domain to exactly one element in the range. So previously, when we talked about functions, we said that two different elements in the domain could map to the same element in the range. In this case, it would not be a one-to-one function, because here we have two different x values, say x1 and x2, that are different, so they're not equal, but they would have the same y value, which is what this is saying. So they would say that f of x1 is equal to f of x2 here, in this case. But again, for a one-to-one function, that's not possible. And we say that this function would be one-to-one, and this function is not one-to-one. And again, it's not one-to-one because we have two different x values that map to the same y value. So there's a few ways to actually check for one-to-oneness. You can check them algebraically by using two different x values, and we'll get into that in a little bit. But let's start with the graph, because I think it's a bit easier to determine if a graph is one-to-one. What we do is use the horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than one time. Now this will look very similar to the vertical line test, and that's because it is. It's essentially the vertical line test, but for the y values instead of x values. First, I'm going to go over the vertical line test again. Remember that for a graph to be the graph of a function, no vertical line can intersect the graph more than one time. In this graph, we have a function. You can see that the vertical line does not intersect the graph more than one time. Now, what we're saying here is that for any given x value, it has exactly one y value as an output. So if the graph doubled back and we actually intersected the graph more than one time, then we would say that this x value has multiple outputs. It maps to two different y values. Well, one-to-one functions are sort of the opposite direction of that. Instead of looking at the x values to determine if it has exactly one output, now we're looking at the y values to determine if exactly one element maps to that y value. So here, we can see that there are actually three different x values that map to this y value. So we'll call these 3 points, or these three x values a, b, and c. In the function model here, we would have a, b, and c all mapping to the exact same y value. And that y value would be whatever this red line's y value is. Let's say y is equal to d. Then we would have d here, this. Now, as we showed here, that's not a one-to-one function. So we can say that this is not one-to-one. The only time that a function is one-to-one is if if any horizontal line intersects the graph at most one time. So if we have something like this, everywhere we move this horizontal line, it intersects the graph one time. This would be the graph of a one-to-one function. Now we also need to be careful when we look at the horizontal line test. Notice that the horizontal line test is done on functions. Now if we have a function, that means it passes the vertical line test already. So we wouldn't use the horizontal line test on something that looks like this. Because it doesn't pass the vertical line test, we already know it's not a function, therefore it cannot be a one-to-one function. Let's do an example. Determine if f of x equals x squared is one-to-one. There's two ways to do this. One way is the way that we just mentioned, the horizontal line test. So if we graph this function, it'll look something like this, right? Now we just need to draw a horizontal line. We see that the horizontal line intersects the graph more than one time. Therefore, we can say that this is actually not one-to-one. All right, now the algebraic way. We leverage the definition of one-to-oneness, which is to say that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. We know that the function is not one-to-one, which we've already shown graphically. We just need to find two x values that have the same y value to disprove its one-to-oneness. F of x1 is not equal to f of x2 whenever x1 is not equal to x2. So we're going to look at two different x values that have the same y value to show that this condition is not met. So I'm going to use a and b instead of x1 and x2 just for a little bit of simplicity. So I'm going to find what f of a is, and f of a is a squared. F of b is b squared. So we have, just by plugging in our a, we get a squared, and plugging in b, we get b squared here. So now let's look at let's assume f of a equals f of b. Now, if this function is one-to-one, that will mean that a has to equal b. Because if a is not equal to b and f of a equals f of b, then this function is not one-to-one. So we assume that it is one-to-one, and we're going to show it's not. Well, this then means that a squared is equal to b squared. We could take the square root of both sides. I think it's actually easier to see if we don't take the square root of both sides, and instead we subtract the b squared over, and we end up with a squared minus b squared, like this, is equal to 0. And then we have a difference of squares. And we get that a plus b times a minus b is equal to 0. So we have either a is equal to b or a is equal to negative b. Well, this causes a problem, because on the one hand, we have a is equal to b is one of the solutions to when f of a equals f of b, and this should be the obvious solution. If a is equal to b, then we would have f of a is equal to a squared, which is clearly the same y value. But if a is equal to negative b, then we have a completely different x value, but they have the same y value. So here, having a equals negative b as a solution causes this function to not be one-to-one. So for simplicity, I'm going to give b a value. B equal 2. 2 is not special. It does not matter what value I choose for b as long as b is not 0. So if a is equal to negative b, then a is equal to negative 2. Now these are clearly two different x values, right? So we've satisfied this condition, which means that this condition needs to be satisfied as well in order for this function to be one-to-one. But if we plug them in, f of 2, which would be f of b, this is equal to 4, and f of negative 2 is also equal to 4. So this condition actually doesn't get satisfied because f of 2 and f of negative 2 are equal, which is invalid here. So this is not true whenever x1 is not equal to x2. So we can say that this function is not one-to-one. All right, I want you to try one now. Determine if f of x equals x cubed is 1 to 1. The next thing that I want to talk about is inverse of a function. Recall, a function applies a rule to an input value. Note, the inverse of a function f undoes the rule that f applies. When introducing functions earlier, we talked about a couple of functions, one being like a printer. A printer would receive a digital copy of a document and then it would print it out. It physically print on a page what the digital copy showed. Now, the inverse of a printer would be like taking that piece of paper and creating a digital copy from it. So almost like a scanner would sort of be the inverse function of a printer. We also talked about a blender being a function. Now, we said that the input of a banana into a blender would output banana mush. Now, the inverse function of that would be something that takes that banana mush, puts it all back together how it was originally, and then outputs that banana. So all an inverse function does is it undoes what the function did. Definition? Let f be a one-to-one function with domain D and range R. Then its inverse function f inverse has domain R and range D and is defined by f inverse of y is equal to x if and only if f of x is equal to y or any y in R. Okay, let me show you a graphic of what this is saying. So suppose that we have a domain and a range, and we have our function f. So our f function is taking values from our domain, applying a rule, and outputting values in the range. Here we're talking about one-to-one functions as stated in the definition of an inverse function. Now, what an inverse function does is it will take values from the range and figure out what its pre-image was. What value did f assign the value in the range? F inverse figures out that value. If f takes this value in the domain and assigns this value in the range, f inverse will take the same exact value and assign this value in the domain, its pre-image in the domain. Just an example. Suppose a function is as follows. Find f inverse. All right, so suppose that we have this function. Let's look at this function here for a second. Our domain are these values. These are the values that x takes. Our range are these values, the values that y takes, or f of x, because y is equal to f of x. So these are our range values. Now each one is assigned to a specific x value. X is 1. Its range value that's assigned to it is 6. If x is 2, the range value that's assigned to 2 is 7. And so on. So if we're looking for f inverse, we're looking to do the opposite. So let's now look at it to find the solution here. Y and f inverse of y. So now we look at the y values. We'll have 6, 7, 8, 9, and 10. And we're going to assign the pre-image value. So 6 is the image of 1. The pre-image of 6 will be 1 because it's the value that is assigned 6 by the function f. So the pre-image of 6 is 1, so we get a 1 here. The pre-image of 7 is 2. The pre-image of 8 is 3. The pre-image of 9 is 4, and the pre-image of 10 is 5. This is a very basic example, but it's meant to show you that the range values are the domain of f inverse, and the corresponding range values are the domain values to which our range values were assigned. So 6 was assigned to 1, which means 1 is now assigned to 6 by f inverse. I want you to try one now. Suppose the function f is defined as follows. Find f inverse of 2 and f inverse of 1. So now you're not looking for the entire function, you're just looking for f inverse of a couple of values. Next thing I'm going to talk about is the inverse function property. Let f be a one-to-one function with domain D and range R. The inverse, f inverse, satisfies the following cancellation properties. F inverse of f of x is equal to x for every x in D. And f of f inverse of x is equal to x for every x in R. Conversely, any function f inverse satisfying these equations is the inverse of f. So first, this is exactly what I was saying before, where f inverse undoes f. So if we compose f inverse with f, then we get back to the starting point. We input an x value into the function f, and then we apply the inverse function, we get back to what we had. Similarly, if we have an x value and we apply f inverse, and then apply f, then we get back to what we had at the very beginning. So an example here. I'm going to try to explain this inverse in a way because we haven't quite learned how to find the inverse of a function yet. That will be in the coming topics. But here, I am stating that f and g are inverses of each other. We're going to apply these functions and show it for sure, but I want to explain this really quickly. So with f of x, the first thing that we do to x is that we multiply by 2. So we take an x value, we multiply it by 2, and then we subtract 3 from that result. All right. Now g should do the exact opposite in the exact opposite order. So if we were to undo f, so think about plugging in an x, multiply that by 2, and then subtract 3. If we're to undo that, we would need to add 3 and then divide by 2, which is what we do here. We take an x value, we add 3 to it, and then we divide by 2. The opposite operations in the opposite order. So here, we're going to look at f of g of x to determine if it actually equals x. So first remember that this is f of g. This is called a composition. It's good practice to have it in this form. F of g of x is equal to f of g of x, which will then be 2 times our g function, 1/2 x plus 3 minus 3. So I've replaced x with the entire g function. Okay. Now if we simplify, then we have 2 times 1/2. Removing these parentheses, we get 2 times 1/2, which is 1. So we'd be left with x plus 3 minus 3 here, which is, of course, equal to x. We can drop the parentheses because we're not multiplying anything here. Similarly, g of f of x, the composition of g and f, is going to be g of f of x in this order. And this means that we take the entire f function and plug it in wherever we see an x in the g function. So we take our g function, we plug in the entire f function, so we would have 1/2 2x minus 3 plus 3, like that. This, in red parentheses, is the f function. I'm only putting the parentheses there to indicate that we are replacing the x in g with the entire f function. But we can drop those parentheses, the red parentheses, and we would have a -3 plus 3, which cancels out, and we're left with 1/2 times 2x. And of course, the 2 and the 1/2 cancel, and we're left with x. So notice that when we composed f with g, when we composed f with g and g with f, we had a starting point x, and our ending value was also x. So it's what we started with. Right, the next topic will be finding the inverse of a function. Recall from about 5 minutes ago, if f is 1 to 1, then f inverse of y equals x if and only if f of x equals y. This is how we defined f inverse. Now I want to give you a guideline on how to solve these types of problems algebraically. How to find the inverse of a one-to-one function. 1, replace f of x with y. 2, swap your x and y variables. 3, solve for y. And 4, replace y with f inverse of x. Let's go ahead and do an example here, where we'll do each of these steps. Find the inverse of f of x is equal to x minus 1 over x plus 2. Now this is a typical function that you'll see. Our first step is to change our f of x to y. So we would have instead y equals x minus 1 over x plus 2. This would be step 1. Step 2 would be to swap the roles of x and y. So we replace y with x and x with y. Now you have to replace every x with y. And 3, we solve for y. 3 is a little bit longer. We need to get y alone. Now, in order to get y alone, we need to get all of our y's out of the denominator. So first things first, I'm going to multiply both sides by y plus 2. So now on the right, my y plus 2's cancel, and I'm left with x times y plus 2 equals y minus 1. Distribute this x, and we get xy plus 2x is equal to y minus 1. Now, in order to get y alone, because I have two terms with a y in it, I need to get all y's on one side so I can factor it out. I'm going to get all my y's on one side, and all my x's on the other. So here I'm going to subtract y and subtract 2x from both sides. And we get xy minus y is equal to negative 2x minus 1. Now I see that I have a y that's common in both terms on the left. Factor a y out. I get x minus 1. And then I'm going to divide both sides by x minus 1. And I'm left with y is equal to negative 2x minus 1 all over x minus 1. And then, of course, you replace y with f inverse of x. So for the final step would just be for cosmetic purposes. Note that my negative is in the numerator. If I wanted to write my negative in front, then I'd have to factor a negative out of the top, and then I could write it in front. But because this negative is specifically attached to the 2 and not to the entire numerator, I need to write it in the numerator here. This will be the answer to this problem, though. These problems are a little bit more complicated than the previous example because you have multiple x's. So we don't do just one thing to x at a time, like we did in this example, where we're multiplying by 2 and then subtracting 3. Here, in the numerator, we're subtracting 1, and in the denominator, we're adding 2. So we're doing multiple things to x all at once. So trying to find an inverse without doing a procedure is a little bit more challenging. Try one. Find the inverse of f of x is equal to 3x plus 4. Just to get some practice, you might want to practice with these types of functions as well. These ones are a little bit more challenging, but these are typical problems that you'll see. I just wanted to start you off on an easy problem here. The next topic will be graphing the inverse of a function. Recall. Remember that f has a domain D and range R. F inverse has the opposite, domain R and range D. Note, if a point AB is on a one-to-one function f, then BA is on the graph of f inverse. So when we talk about graphing a function's inverse, we assume we already know the graph of a function. How this works is the x and the y coordinates are going to be flipped. If we have a point AB that's on our function, then the point BA is on the inverse. And it's simply reflected about the line y equals x. So our x and y values are swapped. This line is of equal length to this line. So if our point AB is on our function f, then BA is on the function f inverse. And this is true no matter what point we look at on f. So remember, as a function f maps out, as a function f is mapped out by a bunch of points, the f inverse will be mapped out by reflecting it about the line y equals x. The graph f inverse is obtained by reflecting the graph of f about the line y equals x. Let's go ahead and do an example here. Here's our graph. All we need to do is reflect this graph about the line y equals x. In order to find the inverse. So if this is f of x, then f inverse of x will look like this. Instead, you just take it and reflect it about the line. Now, notice that any point that's on the line actually doesn't change. So this point that is on the line, y equals x, is on both curves. Similarly, 0, 0 is also one of those points. I want you to try one now. Find the inverse of the graphed function. And I'll give you the line you need to reflect it about. Here. Do your best on this one. Obviously, your graph will probably not be perfect, but give it a try. That will be it for today. I will see you all in the next lecture.